Think of an internal combustion engine, say a diesel cycle. We're not too dissimilar. We're just using magnetic fields instead of physical walls. We're doing a very similar thing, only we have a magnetic piston that is compressing, and we're releasing nuclear energy instead of chemical energy, but it's pushing back on that magnetic piston and driving work and ultimately allowing us to create electricity.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. I'm here with Anthony Pancotti, co-founder and head of R&D at Helion Energy. We'll be talking about nuclear fusion, and Anthony is a perfect guest for this because Helion is in the process right now of building the world's first commercial fusion power plant. Their plan is to be operational and supplying their first customer, Microsoft, by 2028 as part of a power purchase agreement. This is a big deal because fusion, of course, has the potential to create energy from virtually limitless fuel that has crazy energy density without emitting greenhouse gases or long-lasting radioactive waste. I just read today that 1 kilogram of fusion fuel provides as much energy as 10 million kilograms of coal, which is kind of mind-boggling. Anthony has a PhD in aerospace engineering and worked on propulsion research for NASA and DARPA for a decade prior to co-founding Helion in 2016. Since then, he has helped to grow the company from early plasma experiments to over $1 billion in funding and this strategic partnership with Microsoft I just mentioned. Anthony, that's super impressive. Really excited to have you on. Thanks a lot for joining.
Thank you. I'm very excited to be here.
So you started out focused on propulsion and aerospace. I'm curious to hear the story of how that has turned into this focus on fusion.
Yeah. So that's really my story. My background was in space. I was a space nerd growing up. Loved NASA, loved the stars, played with, space Legos growing up, and kind of always wanted to be an aerospace engineer, even in high school. And so I started on that path. I really knew I wanted to do a PhD. I kind of wanted to be at the most cutting edge of technology. I was obsessed with technology. And aerospace engineering, space seemed like the final frontier, right? It seemed like the most hardest, challenging problem for humanity. How do we become a spacefaring race, a multi-planet species? I was just so impassioned by all of that. It's where I got my PhD, and I did study in plasma. So advanced propulsion systems. How do we, once we're in space, how do we travel around our solar system? And I started looking at the problem of living on other planets and how challenging it actually was. And I looked at the time horizons for that. And it really became apparent to me that I wanted to focus on problems here on Earth and actually not try to escape planet Earth, but save planet Earth. And that was really a fundamental shift for me, going from being like a space nerd and wanting to get out into space and really realizing how incredibly unique our planet is, and what a poor job we were being as stewards of that planet, and really wanted to focus more on saving it than escaping it.
Mm-hmm. Yeah, I've seen there was a video or some meme that went around last year or something, like there is no planet B, right? Like with this, we got to kind of figure this one out first.
100%.
Or at least, yeah. Did you, was it clear that fusion was the right place for you to focus your efforts when you kind of had that realization? And is that because it aligns really well with your kind of technical background, or how did you get to fusion?
Yeah, I mean, it was a perfect alignment there. So the company I was working for when I came up to the Washington area, to the Seattle area, the company did space propulsion. It also did fusion. So it was kind of an IP house. It did a little bit of both. I came in through the space propulsion side of things, but they're both plasma physics based. So if you have a degree in plasma physics, there's only really a couple areas you can go into: space propulsion, fusion, maybe some semiconductor processing. But the field of plasmas is kind of small. And that's where I met the other co-founder. So David Curley, our CEO, he was also kind of came out of the aerospace industry. We had met actually back in the day at the Air Force. We were both kind of doing our PhD research thesis. We just kind of met. We were working together up here, half of the company was doing fusion, and it really just started gravitating. We had some really good success with some early programs that were funded by the DOE, the Department of Energy, was funding some basic research into our technology and into our approach. Those results were extremely positive, and that's what enabled us to go out and get venture capital and really scale the company quickly. That's what brought all of us together, was how do we commercialize fusion as fast as possible in order to try to save the planet?
I just, like, even today you hear a lot of people saying, this is 20, 30 years out. Like it's sort of in the, like, is it even possible? Is this realistic? I'm curious, like 10 years ago when you were doing this, it must have felt like such a crazy moonshot, or maybe you knew so much about kind of the kind of technical details that it didn't. I'm curious, like, did you feel like you were getting into something that had, like, very high risk but high return, or how are you sort of making that calculus at the time?
I think that's the exact calculus we were making. It is high risk, high reward. So fusion in general, and I think we've de-risked fusion a lot, and we can get into that as we talk more about the technical and commercial aspects of what we're doing. But yeah, certainly 10 years ago, we were, looking at this problem, and I think all the co-founders were very frustrated by the direction fusion was going. At the time, the majority of the funds and resources were going into large monolithic programs. They were largely science projects to understand fusion and understand ignition. And the time horizons and the scale and scope of these projects really wasn't resonating with us. And it wasn't until we took a step back and looked at the fundamental approach to fusion and how can we make that scalable? How can we make that mass deployable? How can we make that commercially viable with existing technology today? Or commercial off-the-shelf components, or next generation commercial off-the-shelf components. And personally, that's what sold me on the company. That's what got me on board with the other co-founders. It wasn't the physics and the fusion physics and the plasma science. I knew all that very well, right? That's my background. That was my PhD work. But it was really sitting down with David, one of the other co-founders, and going through the economic models, the commercial models, to show how we could do this in a very short amount of time with technology that exists today and make it mass deployable, scalable, assembly line produced fusion systems that we could distribute around the world, that I got really excited and fully got on board with Helion.
Mm-hmm. So, say more about that. What, and I don't know if it's how explainable this is going to be on a podcast, but I'm curious, like, what was it about your approach that made it more kind of commercially viable than what others were looking at the time?
So I think fundamentally one of the key components of that is moving away from steam turbines. So the majority of electricity generation, whether it be from nuclear, from fission, or gas turbines, coal plants, they're all basically using 100-year-old technology of generating heat and then having a thermal conversion system that turns heat into electricity. That is some type of turbine, steam turbine, typically 30-40% efficiency, just rough numbers. But it's all about the heat source. And so a lot of even other fusion systems, whether it be magnetic confinement fusion like tokamaks or stellarators, or laser-based systems, inertial systems like the National Ignition Facility, they're all using deuterium and tritium. They're all looking for sources to generate heat, but they're ultimately running the same turbines. They're running the same 100-year-old technology of converting thermal energy into electricity. Helion is a fundamentally different way of doing it. And what we're doing is we are using a pulsed approach combined with a very unique fuel, which is deuterium and helium-3. That reaction is aneutronic, which means it doesn't produce a neutron. Neutron is the form of energy that comes out of a fusion reaction that has to be converted into heat. It doesn't interact with magnetic fields. The only way to stop it is to embed it in material, let it lose its energy, and then thermalize it. What we're doing at Helion is we're taking a deuterium and a helium-3, and when they fuse together, they produce charged particles. And those charged particles now do interact with magnetic fields. We can interact with them, and we can directly recover that energy back. So if you combine very, very efficient pulse power circuits, so the systems that drive all of these electromagnets, if we can make those at 95% efficiency, which means we recover the majority of the energy back before we even do fusion. And then we produce those charged particles and we directly recover that energy back without having to go through steam turbines. One, it allows for a higher efficiency conversion, but also it just moves you away from turbines. And turbines are these large monolithic infrastructure projects. And if you move away from that, you can think about building power plants on assembly lines and deploying them around the world. The way I like to think about it is building aircraft instead of building airports. That the approach Helion is taking is an assembly line production of a generator, of a device that is mass manufactured, deployed, and turned on. And when you think about that approach to energy, it really just changes the way we need to deploy it. And I've kind of said that, if we build a single power plant or bespoke one-off power plants, it doesn't scale. If we're trying to save the planet from climate change, not only do we have to unlock fusion, but we have to unlock fusion in a way that is rapid enough to impact the damage that we're doing from releasing of carbon.
Mm-hmm. Yeah, this is a very common theme, I feel like, in all these climate solutions, that if you can, and I think this is what you're saying, you're building a product, not a product that can be mass produced and replicated and iterated quickly and cost reduced. You get sort of the economies of scale, as opposed to building large sort of facilities and factories as one-offs. And the common analogy people always draw is like that if you look at how solar scaled, it was by building lots and lots and lots and lots and lots of solar panels, and getting the economies of scale from doing many of the same thing over and over. Is that kind of what you're saying? That's the path to scale with your approach?
That's exactly right. Yep. And it's kind of the modern approach to hardware, that these large infrastructure projects are making less and less sense in these mass-produced, assembly line-produced technologies. Like a great example is solar panels, and getting that economy of scale that really kind of unlocks the ability to keep up with our massive demand for power.
Right. And one of the things about your approach that enables you to do that is that you're not dependent on turbines for converting your energy into electricity that can be put back on the grid.
Yeah, that's one of the major ones, is that turbine is such a large infrastructure piece that it usually has to be designed in the site. And there's a lot of permitting and process and regulatory that goes around siting massive cooling towers, massive turbine systems. They have to be built on location. You can't drop ship them in. So Helion technology is specifically designed to be packaged in standard containers, pulse power systems, fusion cores that can be, the individual components are produced on assembly line, dropped to a site. That site is, for example, Polaris, which is our 7th and final prototype here. It's a standard tilt-up concrete building, Amazon-style warehouse, where we can go deploy that technology in that warehouse and turn it on and start generating power. So part of it is the framework around the technology and how we deploy it. Other aspects of it are the regulatory frameworks that allow you to go deploy systems in months instead of years or even decades for some of the more complicated regulatory environments around nuclear, around fission.
Mm-hmm. And you said too that you're using a different fuel. So you're using deuterium, but instead of tritium, you're using helium-3, I think you said, which I honestly don't know what that is, but I'm curious because one of the advantages people always say about fusion is that the fuel is so abundant and cheap and easy to get. Is that still true with your approach with helium-3?
Yeah, it is. So we produce our own helium-3. Helium-3 in itself is pretty rare here on Earth.
Okay.
But we produce it in our devices ourselves. So a little bit about helium-3. Helium-3 is just an isotope of helium. So the two lightest elements on the periodic table are hydrogen and helium. Hydrogen has isotopes in the form of tritium and in the form of deuterium. And then there's a helium-3, which is an isotope of helium-4, which is the normal form of helium. And we combine in deuterium and helium-3. And that fusion process, what's very unique about it is it doesn't produce that neutron. It produces a proton and it produces an alpha particle, which is the helium-4, but they're both charged particles. And that's really fundamental and key to the approach of how Helion produces electricity is to produce charged particles instead of neutrons. Neutrons are particularly damaging. So it's a ionizing radiation that can cause damage to materials, has some regulatory implications, but it also has lifetime implications as we talk about how long these systems can live and operate. And so having that aneutronic form of fusion has some major advantages. Now, to produce the fuel, we use what's called the side reaction. So the main reaction is deuterium and helium-3. That's what generates the energy that we recapture as electricity. But the deuteriums collide with each other occasionally. And that process of deuterium colliding with deuterium and fusing together, that produces a tritium and a helium-3 that we can use in the future. So we produce all of our fuel gaseously within our system. We have gaseous separation systems that can recover that fuel that we generated and recycle it and put it back in our machine. In the fusion industry, we call that a closed fuel loop. Mm-hmm. And so the only input from our system is deuterium, which is kind of readily available from seawater.
Right. Yeah, I read some other stat. I didn't write it down, but like a liter of seawater has some, enough deuterium to like power a city for a month or something like this. I forget what it was, but like it's like very, very abundant in seawater, apparently.
Correct.
Okay. Very cool. So Polaris, what you're currently in development on, this is what will be producing energy for Microsoft?
Polaris is not. That's Orion.
Okay.
Polaris is our seventh and final prototype. So over the last 10 or so years, we've incrementally increased in our energy density and our power and our fusion output. Trento was our previous prototype. That was the one a couple years ago, made some headlines, some news about reaching 100 million degrees. 100 million degrees is 5 times hotter than the sun. It's the relevant temperature that every fusion company is after to try to get the right temperature to get to fusion conditions to get these very light atoms to fuse together. And so Trento really proved that we could get to the fusion conditions we needed to make a power plant. Polaris is our 7th and final prototype, and its major milestone is to demonstrate electricity from fusion. So this is this process of compressing and expanding that FRC and directly recovering that energy back onto those capacitors again, avoiding the turbines, avoiding the thermal cycle, and doing direct energy recovery. And so this will be the first time that humanity has ever generated electrons from fusion. So lots of other companies have demonstrated fusion, national laboratories. The National Ignition Facility has done phenomenal things about gain and actually demonstrating yield. But yield is just the beginning of the story. You have to convert that fusion energy back into electricity. And Polaris's main goal is to show the processes and the architecture to do that.
Okay. And then people also talk about, and I might get the terms wrong, so help me out, but like ignition, reaching ignition or reaching kind of net gain where your process is producing more energy than it takes to maintain the temperature needed for fusion. Are you also doing that? Or in your prototypes or in Polaris, or do I have that right?
Yeah, there's a little bit of a subtlety difference in gain and ignition. So ignition, you can think of as a process of sustaining a reaction. And so ignition is not something that Helion is pursuing in its technology. Almost all other forms of fusion are. And the idea here is that once you start the reaction, once you get those first initial atoms to fuse together, they release their energy. It further heats the plasma, and that heating process sustains the fusion reaction. You could think of it as like burning, right? It's an ignition process. All of the energy required to reach fusion condition is directly applied by our magnetic fields. So as we're compressing and driving these to higher and higher temperature, it's the magnetic field that is pushing the temperature higher, not an ignition process. And so we do simplify some of the challenges around reaching and sustaining ignition in our systems. But fundamentally, gain is a scientific number about how much energy you put into the system versus how much energy you get out of the system. Now, gain is not equal across all forms of fusion. Some fusion systems need higher gain because their systems are so lossy, right? They have a lot of losses into getting energy into that plasma, so they need a higher gain. They need more energy out of that. Helion is fundamentally a low gain system. So we rely on engineering and pulse power systems and electromagnetic systems that are extremely efficient. So 95% efficient. And what that means is that we can put 100 megajoules worth of energy into this device, and we can recover back 95 megajoules worth of energy without doing any fusion, which means the amount of fusion that we have to do in order to have a surplus is only about 6 megajoules, right? Just, again, these aren't actual numbers, but just for an example, where other fusion systems, they might be putting in massive amounts of energy, don't have the ability to do that initial recovery, and therefore they have to produce 101 megajoules of energy just to get to break even. So Helion systems are relatively small for the fusion space. Very, very efficient drive circuits, very, very low yield or low Q systems in order to close the architecture.
Okay. So that net gain something you've already proven, or is that still on the roadmap for like Polaris or future systems?
So Polaris will demonstrate the electricity from fusion, but won't be a balance of plant, won't fully balance out the system. That will be the Microsoft PPA power plant that we're calling Orion. So Orion broke ground in July of last year. And we've been building the infrastructure and the facilities and getting started on that project already.
Okay.
And that will be a first of a kind demonstrator of a fusion power plant.
Okay. I'm curious to understand more about the sort of physicality of this stuff, of Polaris and maybe Orion too. What does this look like? What are the sort of main subsystems involved? And can you give me a flavor of some of the gnarly technical challenges you've had to tackle to get to this point?
Yeah, I'd love to take a minute and kind of explain the process from start to finish, and I think that'll kind of elicit some of the subsystems.
Yeah, perfect. Yeah.
So the technology is based on something called an FRC. An FRC stands for field reverse configuration. It's basically a fancy term in the plasma physics world for making a magnetic bottle or a plasma bottle. And so in our system, we have these things called formation sections. Formation sections are where we form these FRCs or we form these plasma bottles. And charged particles do not like to cross or can't cross magnetic fields. So if you think about the aurora borealis, why we have those northern lights, that's the Earth's magnetic field, and you have charged particles from space coming in, interacting with our environment, and they can't cross those field lines. They get stuck on them, and they migrate up to the North Pole, and that's what creates those northern lights. So the fact that we have charged particles, we can trap all of our fusion fuel inside these magnetic bottles. And then we take 2 of these magnetic bottles, or FRCs, we accelerate them together, and we merge them into what we call the compression section. And the compression section is the heart of this fusion device. The formation accelerators, you can think of them as just injector systems. But once we get into that compression section, we have this merged and largely stable plasma bottle that is filled with plasma and all of our fusion fuel. And we start magnetically squeezing it down. We apply these very, very large magnetic fields, huge magnetic field coils that compress that FRC. And as it gets smaller and smaller and smaller, the density goes up and the temperature goes up. And eventually you reach a condition where the temperature is high enough and the density is high enough that fusion occurs. And as that fusion reaction occurs, it produces charged particles. Again, because we're using deuterium and helium-3, those charged particles are still trapped within the bottle. And so now you're adding energy to this bottle, and just like a balloon, it starts to inflate and push backwards. And it's this process of compressing and expanding that FRC that allows us to do this direct energy conversion. I think one of the most interesting analogies here is think of an internal combustion engine, say a diesel cycle. We're not too dissimilar. We're just using magnetic fields instead of physical walls. So in a diesel engine, you have a piston or a cylinder and you inject fuel. You inject chemical fuel, and that piston compresses it until you get to the right temperature and density. You release the chemical energy and it physically pushes on the wall of the piston and drives it outwards. That creates work, that creates electricity. We're doing a very similar thing, only we have a magnetic piston that is compressing and we're releasing nuclear energy instead of chemical energy, but it's pushing back on that magnetic piston and driving work and ultimately allowing us to create electricity.
That is a very good analogy, actually. Thank you for that. And this reaches what did you say? 5 million degrees?
100 million degrees is kind of the starting point when you talk about fusion.
100 million degrees?
Yeah.
Okay.
So one of the things that we actually do in our systems is deuterium and helium-3 is the harder form of fusion. So it's all about reaching the right temperature and doing it at the right density, but really reaching the right temperature. And for deuterium and tritium systems, so most other fusion systems, they only need to get to about 100 million degrees, around that 10 keV kind of point. We actually need to go higher. So we're actually doing the harder form of fusion. The reason we're doing it is because of the aneutronic nature, because of the mass deployability of these systems. And so if you look at the long-term success and the need to be mass deployable, getting helium-3 to work really unlocks regulatory pathways, supply chain, and all of the other things that you need to mass manufacture and deploy.
Mm-hmm. Okay. Maybe it's a naive question, but what does it take to contain something that's sitting there at 100 million degrees plus in your system? I mean, like, I suppose it's suspended, right? It's not touching anything. I don't know. Just help me understand how that works.
Yeah, we use the term magnetically insulated and isolated. So it goes back to that FRC, of that plasma bottle. So
yeah,
the temperature, the particles themselves are moving around very, very quickly, but again, they can't leave the boundary of the bottle. That magnetic field structure contains them in the middle and keeps them off the wall. That's fundamentally how we design those systems, is that those particles actually rotate around those magnetic fields. It's called a gyro orbit, but those charged particles are actually moving and they're gyrating around those magnetic field lines. And we got to make sure that the magnetic field line they're trapped on is far enough from the wall that they don't hit the wall. So in our systems, none of that gas, none of that plasma at that temperature touches the wall. It's all contained within a magnetic field structure.
Yeah. What are some of the technical hurdles remaining to get to this sort of commercial deployment with Microsoft? What's on the horizon for you guys to tackle still?
Yeah, there's some fundamental technologies that are built into what Helion is doing. I think primary to that is these magnetic field coils. So building high strength pulsed magnetic fields is an engineering challenge in and of itself. It's not necessarily a physics challenge, it's an engineering challenge. So a lot of the challenges we have left are some of these kind of known engineering challenges. People have built high field pulsed magnets that can go up to many, many tens of Tesla, even hundreds of Tesla, but they don't last very long. They're almost destructive coils because the amount of force and impulse to create these very large high field pulsed electromagnets is limited. And so that's an area of research that Helion is really leading the forefront on. We have a lot of IP, a lot of trade secrets on how to build long lasting, very efficient, high field pulsed magnets. And then the other side of that is the drive circuit that pushes all the current through that magnet, right? This is an electromagnet. So you're driving massive amount of amperage through these field coils. And there's a whole, what we call a pulse power system that has to drive these coils. It's basically the drivers for the entire system. And as I mentioned before, the more efficient we can make those driver systems, those pulse power systems, the less fusion we have to do. So the difference between a 95% efficient circuit and a 96% efficient circuit, well, it's only 1% in efficiency. That's many megajoules of fusion that we don't have to do if we can make those systems more efficient. So we spend a lot of time engineering extremely efficient pulse power systems and very, very large, efficient, long-lived electromagnetic field coils.
So I want to understand more about the business side. And one thing that strikes me as really impressive is the amount of money you've raised. So $1 billion in funding. And I'm curious if you can rewind way back to the early days before you had sort of proven these things out in prototypes and whatnot. What does it take to get investors on board with something that is so unknown and high risk, especially prior to kind of proving all this out through prototyping?
Yeah, the investors for any startup is a really interesting space to think about. And a lot of times young companies are just thinking about getting any money in the door, right? Just to fund the concept. But your cap table and who your investors are your partners. And they play an important role in any young company, in any hardware company. Hardware companies in general tend to require a little bit more patient capital. They're a little more capital intensive, right? Because you actually need facilities to actually purchase hardware. So Sam Altman has obviously played a huge role in being one of the early investors with Helion, and Sam has an incredible vision for the future, right? So those type of visionary investors are extremely important and have been extremely important for Helion and for Fusion. But any hardware company that's trying to change the world has a long kind of time perspective. You could say is a high risk, high reward. You need people that are tolerant of that risk and excited by the vision that you have for the future. And so early on in early days, having those true visionary investors in your company that can support you are extremely important. And then as you reduce your risk, you build out your maturity of your technology, you start bringing on additional investors that may be a little more risk adverse. You burn down a lot of your risk, and it makes more sense for institutional investors or other investors to come along, growth investors that can really help you scale and grow.
And then you've taken it to the point of actually having, I don't know if would you call Microsoft a customer, or they have this power purchase agreement with you. I'm curious. I think that's unique in the industry. I'm curious what you think Microsoft saw in Helion as opposed to other fusion startups or fusion approaches. Like how did that come to be?
Yeah, Microsoft has been a partnership that we've been working on well before we released or got that PPA signed in 2023. And so we had known them for years before that. We have had discussions with them about the technology. They got to know us as we continued to mature that technology. And I think they just saw a lot of the things we've been talking about, and that Helion was not only a roadway towards fusion, but mass deployment of fusion. And as Microsoft looked at their very aggressive goals to decarbonize their entire infrastructure, they really saw Helion as not only a technology that could be demonstrating fusion, but could be scaling with their growth plans as well. And I think that's one of the things that really got them excited about what we're doing.
And do you think that's how fusion will first expand and sort of, powering data centers and big tech like Microsoft? Will those be the first industries to adopt this?
It's certainly been true from our perspective so far. So we do have a power purchase agreement with Microsoft 2028. Next customers are already kind of in line with Nucor. Nucor has been interested in facilities above 50 megawatts at the couple hundred up to 500 megawatt class system. And so they have a green electrical smelting process that they use to produce steel, Nucor being the US's largest producer of steel. And so again, large industrial applications are a great segue, but ultimately fusion needs to be power for all of humanity. Fusion needs to power homes, it needs to power industry, data centers, basically removing carbon load from our entire electrification process.
Is that, do you think that's the future of our energy mix? Is over time, and I don't know how long that would be, over time we gravitate towards fusion everywhere? Do you think we'll always have this kind of mix of solar, geothermal, hydro, or is it does fusion have such an advantage that we'll kind of end up with fusion everywhere?
It's a really good question. And obviously I'm very biased towards fusion and the impact that it can have. Fundamentally, I'll say, especially at this point in time in the race against the clock to decarbonize, we need all hands on deck. We need all technologies giving it their best shot to decarbonize us as fast as possible. If you look at the long game, though, fusion is such an end game technology, right? Fusion is the source of energy for our solar system, for all of the cosmos. All of this energy that we have really ultimately came from fusion. Whether it even be fossil fuels is just a storage of fusion energy that has come from our sun. Wind, solar, right? It's all forms of fusion. So going to fusion is like tapping into the source of electricity and ultimately harnessing it. So there's a lot of power in that as an end game technology. But in the near term and for a large part of our future, yes, we do need as many technologies as we can to help reduce the amount of carbon that we're pumping into our atmosphere.
What about looking at it from a purely like unit economic standpoint? How, and I imagine it changes a lot as you scale up, but how should we think about fusion relative to these other renewable energy sources like solar from just a cost per megawatt standpoint or cost per kilowatt standpoint?
So the goal of the technology, and I think we had talked about initially about the density, the energy density of the fuel, that really unlocks a levelized cost of electricity that is much lower than any of the other competing sources. And that can be natural gas, that could be solar or wind. And so ultimately the goal of fusion and the goal of Helion is not to be the best green energy source, but it's just to be the best energy source, period. And that's fundamentally something that I believe in. The green tax doesn't really get you where you need to be to save the planet. It not only has to be environmentally friendly, but it just also has to be the best form of power, right? And so fusion has the capability to do that. All these different fusion systems really have the ability to produce a base load, abundant form of energy. Solar and wind, they need battery systems to balance them out and all this other stuff. So there's definitely a core requirement for that like base load carbon-free power that really fusion is well suited to hit.
And can you quantify it at all? Is it like orders of magnitude cheaper in theory at scale, or what does that look like?
Yeah, it's on the order of magnitude difference in price. So when we look at the cost of fusion electricity, it should massively undercut or be able to undercut all other forms of generation on the planet. And that's the goal. And that's why, yes, it's the risk is high, but the reward is just so massive.
Yeah. We've talked about some of the kind of technical hurdles you're still working through, or kind of these engineering challenges to address. What else needs to happen? And I don't know if the big bottlenecks are policy or infrastructure, or what else needs to happen to enable this to really scale and start to have that kind of impact?
It's a really good question, and it's one that we think about all the time at Helion. The way I kind of frame it is you need to solve the whole fusion problem, not just the technology. And what that means to me is you need a very, very clear regulatory framework to go deploy, and you need a supply chain that is scalable with your technology. And if you solve the technology problems, but you still had regulatory problems and you still had supply chain problems, you're not going to be able to achieve what you need to achieve. And any one of those is true. You need all three of those things to happen. So many, many years ago, even as our technology was maturing, we went out and started working on the regulatory components. So Helion had an important role in getting fusion regulated more like particle accelerators and not like fusion reactors. And so the NRC came down and made a judgment that fusion will be regulated by the state. And so we are currently regulated by the Washington State Health Department to guide us and help us deploy these systems. Again, just setting that framework up to set the time scale of how we can deploy these systems quickly. So that's been very, very beneficial. And then the supply chain is another big one. So very core to the technology and the approach that Helion is taking is to not use rare earth metals in our design. Don't use equipment or supplies that are limited in our ability to get them, because you're ultimately going to hit that roadblock of supply chain. So we spend actually a lot of money. Our last round that we raised, $425 million, the majority of that money is actually going into manufacturing for capacitors and switches, some of the major components that we use to build those pulse power systems. Because if we spend all this effort to prove the technology and then we don't have that ramp to deploy quickly, yes, you demonstrate your technology, but now you're waiting years and years for the supply chain to catch up to where you need to be. And so again, thinking of all three of those things, the technology itself needs to be validated. The supply chain needs to be there for rapid deployment. And you need a regulatory framework where you can perform and move quickly. And Helion kind of addresses all three of those in parallel and has been since its inception.
Got it. The supply chain just for the materials you'll need to produce the actual generators.
Exactly. So if you're using, very limited superconducting materials that are hard to produce, hard to source, like that's just, it's going to be a limitation in your ability to scale.
Yep. And then the supply chain for the fuel, is that a challenge at all, or what does that look like?
Yeah, I think we talked a little bit about that closed fuel cycle. And so for us, it's a fairly
so it's just the deuterium, right?
It's just the deuterium, which can be distilled from seawater. Very robust technology that exists to do that. And then if we close our own fuel loop and produce that helium-3, the fuel is closed, and we can make it ourselves.
So does that mean these should be built near oceans, like on the coast, so you have access to the seawater, or is that not really a consideration?
No, we have, like, on our conference room, we actually have these bottles of heavy water, deuterium, and it talks about how many homes for how many decades of fuel. So the actual energy density of that fuel, it is literally a bottle of heavy seawater that can fuel these power plants for many, many years and for many, many hundreds of megawatt hours. It's not an issue. The energy density, the energy density of the fuel is so high that transportation of fuel is not an issue.
Yeah, it's so crazy. And that actually reminds me of another benefit people talk about with fusion, is that it's kind of geography independent. It can work equally well anywhere in the world. To your point, it's not dependent on weather. We can get the fuel to any part of the world. So it kind of promotes, energy independence and equality.
Yep.
Yeah.
We don't need the sun to shine. We don't need the wind to blow. We don't need to be near, a geothermal activated area. We can deploy these systems anywhere. And unlike nuclear, the amount of space and acreage they take up. So fission is also very energy dense, but because of the regulatory around it, they need very, very large swaths of lands. There's security issues. There's NIMBYism, not in my backyard. So we get to move around a lot of those challenges as well. And we can put these systems on pretty small parcels of land. Buildings that are on the order of 100,000 square feet can house fusion generators that produce hundreds of megawatts worth of power.
Yeah. Thinking about timelines, so you've announced 2028 is when you expect to be delivering power under this power purchase agreement with Microsoft. What kind of timescale should we be thinking about for more broad, availability of fusion power on the grid?
So the entire goal for Helion and our plan is to make that timeline as absolutely short as possible. And I think there's going to be a very long road to 2028. But the whole plan is, once we've demonstrated that technology, that we have the regulatory and the supply chain to accelerate very, very quickly. So I think you're going to see one power plant, and then I think you're going to see 2, 10, 100. And the ultimate goal of the company is to produce a gigawatt per day of capacity and add it to the grid. So if you look at the amount of terawatts of power that we use per year, in order to replace the entire grid worth of fossil fuel burning power generation and replace that within a decade, it does require the scale of about a gigawatt a day of capacity in order to replace the entire grid within a year. And so you look at those ambitious goals and you look at having to ramp up to that speed. And again, mass manufacturing, no supply chain issues or limited supply chain issues, regulatory frameworks that work, and being able to build these on assembly lines. You can think of this as like a gigafactory, where you build these large factories, they're producing all of this equipment, and you are going and establishing these in any corner of the planet that you need power. And that's the goal. It's an ambitious one. It's an extremely ambitious one, but honestly, I think it's the one that is required in order to save the planet.
Amazing. I'm curious if you think about this, but what does it mean for society, for humans, for the I guess the planet, to have access to so much clean energy that's so cheap? Like, how does that change our lives or our economy? I don't even know where to take that question, but it just feels like a total game changer.
This is my favorite
if
question.
We actually achieve this. Okay.
This is my favorite question, because I'm a futurist, right? I'm somebody who thinks about the future. I love the future. I'm also one of those people that is constantly disappointed by the day we live. But we don't have flying cars, right? We don't have all these things. The future I envisioned as a child is not the future we have today. And I always want more and better for our future. And what I think about fusion and what I think about what it unlocks desalination, right? If power is that cheap, water doesn't become a problem anymore. You can think about fertilizers, decarbonizing fertilizer processing. You can talk about carbon sequestration, which is one of my favorites, because when you think about what we may have to do to not only stop climate change, but to reverse it, things like carbon sequestration may be a necessity. And where do you get the power? How do you have the abundance and cheap power in order to run those processes? And you really need fusion to be able to do it. So fusion, in my mind, changes everything about how we approach the economics. It's another way you could think about it. It's almost like a second industrialization for humanity. Then when we first invented electricity and got abundant forms of electricity, we had this industrial revolution, right? Fusion is could really introduce a second age of industrialization where electricity and power is so cheap, so abundant, and so available that we as a species completely change about how we think about using power, that we're no longer limited by the economics of desalinating water, that it's possible.
Mm-hmm.
And that's the future I want to live in. That's the future I see with an abundant, clean source like fusion.
Yeah. Yeah, the carbon removal example is a really good one because I've had a lot of guests on the show talking about direct air capture and other forms of carbon removal, and one of the big barriers is just the energy requirements to do that. And you've seen DAX facilities getting canceled because now data centers are demanding the power that was otherwise allocated for them, and this kind of thing. But yeah, just if energy's cheap and abundant, just throw it at that problem and suck a bunch of CO2 out of the air.
Yeah. Yep. And again, it's an economic proposition. I mean, for me, it's an environmental proposition, but if the damage due to climate change on our infrastructure and on our systems is larger than the cost of recapturing, I mean, it might make economic sense to go recapture carbon to reverse those processes. I think we're a ways away from figuring that all out, but it may be an inevitability. And if we have the power to recapture that carbon, we should be prepared for that.
Yeah. Crazy. I'm ready to move on to the last few questions, unless there were any other things you wanted to hit that we haven't talked about.
No, this has been great.
Okay. So I have 3 questions I ask everybody at the end of each episode. The first is, how optimistic or pessimistic are you about the future of the planet and why?
So I'm very optimistic for our future. I think I talked about how I'm kind of a humanitarian, I'm a humanist, and I am a futurist. And so I really believe that humanity is capable of incredible things. And it seems to be our story that we don't really perform into the last minute, that we're kind of put into this crisis mode. And we are phenomenal problem solvers. That is the strength of humanity, is its ability to solve problems. And as we get closer and closer to those deadlines and those problems become more and more looming, that's really when people step up and they perform and they solve those problems. And so, we're very late in the game on stopping climate change. I don't think it's possible to stop climate change. We can try to mitigate the damage that's going to occur. We can try to reverse some of it. But I do think humanity is going to step up and it's going to solve some problems. And I'm very optimistic for our future, for humanity and for our planet.
Who is another company or individual doing something to address climate change that's inspiring you?
So there's a long list of companies. I am blown away by the vision and the passion of clean tech founders. The entrepreneurial space in the clean tech world is filled with some of the most passionate, driven people that I've ever met. I really like to think about the technologies that fusion obviously enables. So whether that be carbon capture, and again, I think you've talked to quite a few of these companies that are really thinking about the future and thinking about how we actually reverse climate change. Summit Nanotech is a company that's doing direct lithium extraction processes as we think about, mobilizing an electric future. How we get resources such as lithium will be extremely important, and then recycling those battery systems So Redwood Materials is doing some great things in this space as far as how we actually reuse a lot of this limited materials that we have available. And then people thinking about our grid. So our grid is fundamentally broken as well. And so there's some amazing companies like Heron Power out there that are really modernizing a grid for the 21st century and are doing some incredible things. So there's a whole group, there's a whole swath of people out there that are having a vision of a future that is cleaner and more sustainable. And I think there's just a plethora of people that are going to help really change the world.
Yeah, awesome. What advice do you have for someone not working in climate today who wants to do something to help?
I would say get involved. We need the best of us out there shaping our future. And if you have a vision of our future that is different than what we have today or the trajectory we are on, you should be out there getting your ideas out there. You should be finding a partner, a co-founder to help you with your idea. You should be talking to investors that may be interested in funding your idea. And so I would say get involved. The clean tech space is a phenomenal community of passionate visionaries who want a different, better future for humanity. And I think if you sat with your ideas and thought about the future you want and you started talking to people, you'd find a lot of open arms out there.
Yeah. Yeah, totally. I've seen that too. It's very, very welcoming and kind of collaborative community. Awesome, Anthony. That was super fun. I learned a lot. I'm really impressed by what you're up to. Thanks a lot for your time.
Yeah, great. Dylan, I really appreciate it.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.